Hello, calculus fans. Okay, so let's start with this definite integral, the integral from 1 to 4 of x cubed minus 5x dx. We'll do two things. We'll estimate this integral using a left-hand Riemann sum with n equals 6, and then we'll evaluate the integral using a limit of a right-hand Riemann sum. Now, part A is going to give us an approximate answer. Part B gives us the exact value. Okay, so let's deal with part A, where we're going to do this estimation. So when n is equal to 6, we've got a value of delta x. It's 4 minus 1 over 6. Remember that this is b minus a over n, and b and a are the upper and lower limits of integration. So that gives us a delta x equals 1/2, and that tells us what our partition points are. So we start at the lower limit, and then we just keep adding delta x. So to go from 1 to 3/2, we're just going to add 1/2. And each time we move along for these partition points, we're just going to add 1/2 each time, until eventually we're going to hit the right endpoint, which is 4, the upper limit. Now we're computing a left-hand Riemann sum. So that means we need to evaluate the function at the left endpoint of the subintervals. So these are the partition points, which create 6 subintervals, but we want the left endpoint of each of those subintervals. And so that's why we're going to take 1 up to 7/2. So we're not going up to 4 because the last subinterval is 7/2 up to 4, so we want the left endpoint of that. Now we're going to let f of x equals x cubed minus 5x. That's the integrand. So now we're ready to write down our Riemann sum. Now let's start by writing this. L of 6 is equal to f of 1 plus f of 3/2 plus f of 2 plus f of 5/2 plus f of 3 plus f of 7/2. Those are the left endpoints of the subintervals. That's the first 6 partition points. Then, of course, we have to multiply everything by 1/2. That represents the width of the subinterval. If we plug everything in, then we get this gigantic mess. It's so big I couldn't even fit it onto one line. And if you work everything out, it all comes out to 243 over 16. Now again, keep in mind what this is representing. This is an estimate. It's using the left-hand Riemann sum. We're not computing a limit. We're just fixing the value of n equals 6 and estimating with rectangles. And remember that some of these rectangles might go below the horizontal axis, so you might have some negative values in here. They're not negative areas. We're thinking of this as a signed area or a difference of areas. Now, part B is going to take quite a bit more work. So what we have to first write down is a limit of Riemann sums. Now we're going to use n subintervals, and we know that the width of each subinterval is going to be delta x, which is 4 minus 1 over n, and that's 3 over n. We can also write down what our partition points are. So the partition points always start at 1, and then every time we move over to the next partition point, we have to add delta x. So partition point x0 is just going to be 1, and then x1, we just have to take 1 and add delta x. We're starting at 1 because that's the lower limit of the integral. When we work all this out, this is partition point k. Okay, so the right-hand Riemann sum is sum where k goes from 1 to n of f of x sub k times 3 over n. This part here is the delta x. Okay, so now we can plug the x sub k into f. Remember that f of x was x cubed minus 5x. So we should get something that looks like this. Now what I really want to do is plug in these values for x sub k. Okay, so when we do that, we get a sum that looks like this. Keep in mind, we haven't taken a limit yet. We're just computing what r sub n is. This is the right-hand Riemann sum for n subintervals. All right, now we're going to do a little bit of algebra. What we really want to do is work out what happens when we cube this. So if we cube that, then we get an expression that looks like this. Notice I've also distributed this minus 5 into here. And then there's some like terms that can be combined. Like you should see the 1 and the 5, that got combined into a minus 4. And then let's see what else. The 9k over n and the minus 15k over n give us a minus 6k over n. We'll distribute the 3 over n, and now we get this expression. And then the last thing I want to do before we do some other work is just run this sum through each piece. Basically, it's going to look like this. The sum can go onto each piece that we're summing. And then we'll work out each one of these sums separately. Now in the last section, I gave you a bunch of summation formulas like this, and here's where we're going to use them. We're going to take each one of these pieces up here and evaluate what they are with the help of some of these summation formulas. Okay, so we're going to start with this piece here. Now that piece does not require any summation formulas because there's no k that you see in here. This has no k in it, so you're just adding that up n times, so you just end up with a negative 12. Now the rest of these are going to require some summation formulas, these ones here, to help us out. And so these others are going to require these summation formulas that we're talking about. So let's see how this works. With this first one, I like to factor out anything that doesn't have a k and pull it in front of the sum. And then if you go back and look at that first summation formula, it tells us that this expression here can be rewritten as n times n plus 1 over 2. A little bit of simplification. N can be canceled, a 2 can be canceled, and we're left with this. All right, I'm just going to leave it like that for now. Let's go on to the other ones. Okay, so the third term looks like this, and we'll do a similar thing. Pull out the 81 over n cubed because that has nothing to do with the k. And now we'll use a summation formula to evaluate this. All right, so the formula looks like, the formula for the sum of k squared looks like n times n plus 1 times 2n plus 1 all over 6. That's the second of those formulas that I had given you. A little bit of cancellation, and we're left with this. Okay, one more like this. Here's the last term. Same game. Pull out the 81 over n to the fourth. And again, we have a summation formula for k cubed. So that sum of k cubed turns into this. And again, we'll do some cancellation. And we're left with 81 times n plus 1 squared all over 4n squared. You can see that the n squareds cancel. Okay, let's go back now and put all of this together into one expression. So we calculated this for r sub n, all these sums put together, and now we're going to replace each one of them with the corresponding simplified version that we had calculated above. So for instance, we've got this piece here, which we're going to replace with this. And we'll do that for all four of these. We've calculated a simplified version for each one. Okay, so here's what we get just by replacing all those pieces together. Okay, now again, we have not yet evaluated a limit because a definite integral is really a limit. All we've done is some simplification to tell us what r sub n looks like. Now we'll evaluate a limit. So in order to evaluate the integral, we're going to take a limit as n goes to infinity of this expression that we came up with. All right, so the integral from 1 to 4 of x cubed minus 5x dx is the limit of r sub n. And we're going to put this giant expression that we came up with for r sub n in here. And we get this. Now here's a place where some of our work that we've done previously really helps us out. We can just focus on highest order terms. So for instance, this limit down here, the highest order term that we see in the top is at 81n squared, and then there's a 4n squared in the bottom. Think about this one here, a little bit more complicated. If you multiply it out, the highest order term that you see in the numerator will be 54n squared. And then in the denominator, there's a 2n squared. And so if we do that for each one of these pieces, then we're able to pretty easily write down what the limits of these things are. We just end up with negative 12 minus 9 plus 27 plus 81 over 4. Keep in mind, on this piece, the highest order term in the top is 54n squared, and then we have a 2n squared in the bottom, so that's how we end up with 27. And if we work that out, then we get our final answer, which is 105 over 4. That's the exact value of the integral. The first piece we came up with gave us an estimate. This is an exact value because we've computed a limit. And because we're able to compute the limit, that's how we know that this thing is integrable. We also know it's integrable because the integrand is a continuous function, but we're able to directly see that the limit exists, and so that's how we know it's integrable. We spent a lot of time early in the class computing derivatives using the limit definition. And ultimately, we ended up with simpler ways of computing these derivatives. And so, just as we did with derivatives, later on we're going to come up with a much simpler method of evaluating these definite integrals. Okay, that's all for now.